We're continuing with the presentation from Dr. Jessica Granderson on transforming building operations with self-correcting controls technologies. Just a few things about Jessica. She has been working with the Best Center for years, and it's always a delight to hear her. She is a staff scientist at LBNL for many years, and currently is filling in for Marianne as the interim division director for the Building Technology and Urban Systems Division. And she's a member of the whole Building Systems Department. She has a PhD in mechanical engineering from UC Berkeley and an AB in mechanical engineering from Harvard University. And I think what's really important here is that her research focuses on energy management and information systems, fault diagnostics and control, and advanced measurement and verification. I think that's what her topic will be focusing on this morning. There's a lot of talk about AI and AI infiltrating building controls, and I think that will come into play in your talk as well. But with that, let me turn it over to Dr. Granderson. Thank you so much for being here this morning.
Thank you, Peter, for the warm introduction and for having me. It's always a really nice way to kick off the year, really, to be able to address this group and share our work with you all. So I'm excited to be here. I know it's the start of a new year when it's time for these best presentations. So let me get into full screen mode here. Great. I want to start with a little context around recognizing our collective experience in knowing that our commercial buildings routinely fall out of tune. And this has impacts of driving up greenhouse gas emissions in our utility bills. It has adverse impacts on occupant comfort and equipment health and life, and it really hinders our ability to effectively coordinate our buildings with an increasingly clean electricity grid. The impacts nationally are tremendous. We have 29% savings potential just from getting our controls and equipment faults resolved. That translates also into 19% peak load shed potential that's being left on the table, and it translates into bottom line excess of costs to our businesses of $17 billion a year. I'm going to focus the talk today on work that we're doing to enhance fault detection and diagnostic technologies. And so just a couple of words to ground us in what these technologies do. These are software-based information technologies that typically ingest data from either interval meters, certainly from building automation, those central control systems, and sometimes other devices. They centralize that data and execute continuous analysis of the time series. And that allows us to identify problems with the control and equipment operations. So things like you are not economizing when you could be, because perhaps dampers are stuck in a certain position and frozen, or sensors are have drifted and are out of value, or valves are leaking, so on and so forth. And I show here a couple of screen caps on the right of what the interfaces of these technologies look like. The top is showing Sky Foundry's SkySpark platform. So each of those color-coded areas are indicating problems typically across a whole portfolio of buildings that have been identified automatically through the system analytics. On the bottom, I show screen cap from Coppertree's Kaizen tool. That's actually showing how faults can be prioritized and displayed to users, and also quantified according to their utility bill impacts. Now, prior work at Berkeley Lab has really closed the book on the question of how cost effective are these technologies? How do they save? How much do they save? We conducted a study over 100 organizations using these technologies that amounted to an install base of over 500 million square feet, thousands of buildings under management through these analytics technologies. And we found that if you look at a before and after implementing the analytics and after implementing the analytics, users saved on average 9% in portfolio energy consumption across their buildings. And they did that with rapid paybacks on average under 2 years. So the software's out there, it's being used in our buildings increasingly, it's cost effective, it automatically identifies problems. However, people have to fix those problems. And in the business as usual case, this is really a pretty manual process involving multiple actors. And it can take weeks to months and even longer to actually close the loop on fixing a problem once it's identified. So, the graphic here shows that business as usual case. The user of the analytic tool sees that there's a problem, they're alerted, and they're going to have to issue some kind of work order, often bringing in someone to reprogram the BAS to fully resolve the issue. After which point they can confirm through software automatically that the problem has been resolved. So through support from the Department of Energy, our team was able to work with the nation's leading fault diagnostic providers to develop and implement in product the first technologies that can not only automatically find those problems, but can also automatically fix them. So we've been working to date with Clockworks Analytics, Copper Tree Analytics, and with the Sustainable Berkeley Lab team and their implementation of the SkySpark system. Through this work, we're now able to kind of short circuit that process of taking corrective action. So now through a operator approved automated response, we can find the problems, we can execute corrective action and confirm that the problem has been fixed, and do that in a matter of hours with minimal need for staff time. So this really brings together control and diagnostic capabilities, and that does a few things for us. We can free up staff time for the hardest and most interesting problems that merit their attention. We can keep those in-tune operations persistent over time. And there's a point that I'm going to come back to, but I just want to seed it for you now, that this gives us the capability to scale the delivery of low carbon and demand flexible buildings, because we have a software-based infrastructure to leverage that complements what the building automation system is doing. We've done this architecturally in the following way. On the left, I show the historic architecture of these systems. The analytics reads data from equipment and control systems. It kind of operates in a passive manner. It analyzes the data and surfaces that for a user. What we've done is open up two-way capability between the analytics and the building automation system. So we now no longer simply read from, but also can write back to the control system. We've also complemented the fault detection and diagnostic logic with corrective logic that's based on building controls and engineering principles. So in doing that, we've brought together analytics and control optimization. We've focused in this work on really the most common and the most impactful controls problems that we see time and time again in our facilities. And we can apply this to smaller buildings with packaged HVAC systems, as well as the larger buildings with the built-up systems, so long as they are running the FDD software in the first place. When I say we can correct problems, I'm showing in the bulleted list on the right what we're actually talking about. Economizer lockout temperatures, incorrect schedules, releasing manual overrides that are no longer needed, correcting biased sensors. I'm going to show 3 examples from the field on automated loop tuning, implementation of best practice reset strategies, and suppression of rogue zones. And we've also looked at implementing zone temperature set point setbacks in an optimal manner. We've made it through several rounds of iterative field testing, actually across 5 different building automation systems at this point since I created this deck. So we've done this at Emory University with Delta and Siemens Systems, at Schneider Electric's headquarters with Schneider EcoStructure, and at Berkeley Lab on automated logic and JCI Metasys systems. I want to give you all a few examples of what we found and how we did this in the field, building from a presentation from Chris Wyant, who's the ongoing commissioning lead here at Berkeley Lab. So this was all implemented through, these examples will come from the Sky Foundry fault detection system. The first 3 strategies that the team at Berkeley Lab wanted to implement were the set point optimization, rogue zone suppression, and the loop tuning. And these were seen as big energy savers and widely applicable across the campus. The set point optimization and rogue zone suppression was allowing us to apply the best in class kind of sequences of operation, and also enhance the existing logic of the building automation system. In the loop tuning, there's implications there for equipment life and stabilizing the controls across different systems and reducing those hunting faults. So I'll start with the reset strategies. We've implemented automated routines. So kind of with the push of a button, we can deploy 2 different types of BAS. The guideline, ASHRAE guideline 36, standardized trim and response to do supply air temperature and supply air pressure resets across air handling units. And so in these plots on the right, I show on the top the cooling set point in blue, the supply air temperature in black on the top, and on the bottom, in red, the cooling requests throughout the course of the day. The x-axis shows a 24-hour period of operation. And so what you can see is that when we hit that button and said, implement the best-in-class reset strategy, it worked. So you can see that as the cooling requests increase through the morning and into the afternoon, we're actually decreasing, kind of dropping that set point. And you can see how the supply air temperature follows. Between that 2 like afternoon period, you see a little bit of modulation of those temperatures in response to the fluctuation in cooling requests. And then you see the corresponding response at the end of the day as the cooling requests drop off, and we again rise back to those unoccupied conditions. Now, this was implemented in tandem with routines to ignore or suppress cooling requests from rogue zones. So those are actually identified through some of the faults that we know we can detect with these types of technologies. So if we know that the zone has a leaking reheat valve, or the airflow set point's not being met, or the cooling set point is far too low, then we're just going to discount those cooling requests. And that's actually shown on the bottom plot in the darker black shading. So those are the zones whose requests have been discounted. And the result of this is that we can save significant amounts of energy. We're avoiding chilled water use in cases where that excess consumption wouldn't have done any good in bringing the temperatures to a comfortable place for the occupants anyway, because the zone was incorrectly driving things up to an artificially high level. The third example I want to show, so those first two are kind of in that optimization category. We're finding problems, we're improving energy consumption by ignoring the rogue zones, and we're implementing the very best in class reset strategies. This is an example of correcting a fault, the hard fault being hunting from a controller. So we're automating the process of tuning the PID loops here. So on the top plot, you will see discharge air temperature in blue and the temperature set point in black. On the bottom, you see the command status of the reheat valve. So the first thing you see in the red is that valve going open, shut, open, shut, open, shut, just really oscillating. And you also see in blue that we're bouncing all around that set point. So what we did was then, what you see in the middle of the plot, implement a routine to conduct active testing, identify new tuning parameters for that PID controller. We push them to the BAS. And then on the rightmost portion of the plot, you see that the after effect. We've stabilized this controller. The valve command is more steadily modulating throughout the day. And on the top plot in the blue and black, the actual discharge air temperature is better tracking the set point. So a couple more words on how we do this. The fault diagnostic tool identifies the fact that we have hunting here, that this valve is doing the open, close, open, close, open, close thing. We then go in and we perturb the system actively through that read-write BAS capability. We measure the response. So here we're looking at the process variable and the control parameters. Then, with the knowledge of the specific PID equations that are configured for this controller, we can calculate the improved tuning parameters. And we push them back to the BAS through this two-way capability. The test then ends. We're able to confirm through the software that we have indeed eliminated that hunting condition. So I want to kind of zoom back out to big picture. What I hope I've given you so far is a sense of the state of fault diagnostic technology today, how we're enhancing its capabilities, and a couple of examples from the field to show you how it really plays out. Here, what I want to recognize is that going forward, why this work is so important and how this is key to the future vision of where we're driving with building operations. So we're at the precipice of really historic generational investments in our buildings. We have the bipartisan infrastructure law and the Inflation Reduction Act that are keying up those investments. And we know that we need the fault diagnostic technologies in place to ensure the persistent performance of those improvements and enduring value of the investments. The other thing that's going on in the industry is that we have a retiring workforce, and the next generation is going to expect, as we do in every other facet of our lives, that we have access to networked intelligent systems. And it's these technologies that give us the automation and the modern tools that the next generation of O&M professionals will really expect in the work that they do. Broadly speaking, we're seeing this real mobilization around climate urgency, and that's coming with increasing asks of our buildings. So we are really attuned to the role that buildings play in delivering healthy indoor environments, in connecting with a clean grid. And we're looking at pulling in and controlling our buildings in concert with distributed energy resources, with the rooftop solar, with electric vehicles, with battery storage, and doing that all with an eye to minimize greenhouse gas emissions. So that's a complex landscape, and the analytics and optimization technologies that we're working with here give us a mechanism to scale across all those different devices, data models, and equipment configurations. They also, with luck, happen to provide us with this rapidly growing footprint in our stock of software-based infrastructure that we can use as really the pipeline to deploy increasingly sophisticated control strategies across our stock. So I want to end with a couple of back on this schematic diagram to remind us that this is really how we open the door to transforming how we operate our buildings. We're coupling robust analytics with corrective optimal control. And we're doing that in scalable software that can really augment the building automation systems that we have doing the workhorse activities of the control in our facilities. I showed you some examples from the field. This work continues. We're bringing in more buildings, more early adopters of this work, more technology partners beyond that initial set of the 3 FDD platforms. And we're also pursuing additional strategies. So we're bringing into the fold demand flexibility and demand management, as well as automated functional testing. So I'm going to thank you for your attention this morning. I'm going to break here. I'll leave you with our website where you can learn more about this work and open it up for any questions that folks may have.
Yeah, we just have a few minutes for questions, and I feel like we've just scratched the surface of what you're doing with FDD. My one question that I have, and we don't have any in the chat at this point, but thank you for this amazing presentation and sort of a snapshot of where we are and where we're going. Can the FDD detect sensor drift?
Yes, it can. And that's actually one of the corrective strategies that we have developed and then implemented with some of our partners in product here. So not every type of sensor error can be detected, but drift is indeed one of them. And so we can basically write back corrected values, adjusting for drift of a certain, specified number of degrees.
Yeah. Hadley Hartshorn asks, have you found the need to tune control loops more than once?
There's more than once, meaning like in a certain controller, or there's more than once, meaning like multiple controllers across all of the buildings in your portfolio. That latter is certainly the case that we expect. This is an incredibly pernicious problem in our buildings. That's actually the hardest and most difficult strategy that we developed, where I would say we have a certain configuration and success there, but there's much bigger space for us to continue pressing on that front.
Alice LaPierre at the city of Berkeley asks, how does this work with existing BAS? How does this work with existing BAS, such as Delta or Atherton, are you looking for partners who have large buildings with these kinds of systems to serve as test beds or to engage with?
Yeah. Hi, Alice. Thank you for the question. We have deployed this with the combination of copper tree analytics working in integration with a Delta control system. So we understand how that works. And we are looking for expanded field testing and deployment. So we would welcome working with others to expand the floor area where we have these techniques in operation.
And obviously these systems work cross platforms.
Correct.
Yeah. Well, I think that's all the time we have. And thank you for this amazing presentation, Jessica. It's always a pleasure to have you here and to hear the latest research. And in this case, really beginning to improve operations and begin to get the results that we've been hoping for a while. Thank you so much.
Thank you for having me.